Thank you all for your time. I hope it will be about 40 minutes of nice time that we will learn about some new things, hopefully. Like Eric said, I'm interested about fractals, and I'm interested in particular about modeling processes in general, whether you talk about physical processes or cyber processes or cyber physical systems. But I wanted from day one to take a different path and do different things that people are doing in system identification. So the one thing that you will see throughout the presentation is that I will not try to postulate that model. I will have a few words saying that I want to let the data speak the model, and I want to do exactly like what Newton did, basically looking at how the apple falls from the tree and try to infer the dynamical equation from the data. I will not say how I do it now, because I hope it will become clearer throughout the presentation. I will skip the introduction of what a cyber-physical system means, because I hope that everyone is aware here in a CPS group. But basically, the structure of the presentation today will be focusing on two parts. You see the medical CPS right there, and then the multiprocessor systems on chip at the bottom of the slide. The reason is that I choose to do it this way such that you can see the historical way in which I looked at the problem and how I developed the mathematics, how I reasoned from simple to complex, and how I tried to overcome some of the things that the data pose on us. So I will talk about this mathematical modeling of physiological processes, about this new type of physiological aware control, or fractal control that I call. This is probably something new, because it didn't exist, for instance, the time-dependent optimal control and so on. And then I will show how this mathematical framework can be applied to a real system to solve an important problem, for instance, to save power or do power management and so on. Then at the end of the presentation, I will give a brief overview of the things that we tried now. But before that, so before proceeding into the core of the presentation, I want to give you an idea of the problems that we are working on very, very superficially. So this is one picture, probably summarizing the best, in the best way, the research that we are doing in my group. We start from the data. The data can represent genomic processes, proteomic processes, even metabolic, so basically patches that you can put on the skin and can tell you the chemical structure of your perspiration rate, all the way to physiological processes such as heart rate or blood glucose. And you can measure the blood glucose in many non-invasive ways. One is the Google Glass that you see there at the top of the slide. But what we actually do here, we take the data and we try to construct mathematical models, dynamical equations. Whether those equations resemble to the ones that exist in the literature, that remains to be seen, or they are new equations, that is even better, because we come up with new mathematics. So some of the processes that we are looking for. We, of course, model physiological processes. We also model the interaction between bacteria or the interaction between cells. We are interested to model the molecular communication between bacteria, for instance, when they try to do a particular task, let's say drug delivery. So all those are very interesting to us. For instance, one problem that would be I have studied in the past and I'm interested to study further is why stem cell division times exhibit fractality, why stem cell division have certain decisions, like I divide now to specialize in a certain function, and so on. So that would be in the first research thread of mathematical understanding, mathematical modeling, and so on, determining the basic principles behind biology. The second research thread is on the right-hand side. So you have taken this data, you have done the analysis, you have constructed a mathematical model. So then what? So for instance, in many situations, you have to fight either antibacterial resistance, meaning there is a bacteria that adapts very, very fast to your antibiotics, or there are certain viruses that adapt very, very fast, like, let's say, HIV. And you want to find out either a cure or a treatment that can keep the virions within a certain range. So for this, we developed networks on chip-based multi-core platforms that can either perform a stochastic simulation, so more like n-body simulation, but this is in the biological world, or solves a control problem to determine, let's say, the amount of engineered cells that you see here on the bottom left-hand side, which can be injected in the body and keeps the infection low or kills the infection completely. Okay. So these are the big problems that we are looking for. But I was in the first few days as an assistant professor, and I was looking for a problem, of course, with an impact, but an interesting problem for a theoretician as well. And if we look at healthcare, you might have heard that the costs are significantly high. They grow by the year. And right here on the right-hand side, you will see a graph that I only plotted. So do not condemn the CDC. I'm responsible for this. But what you will see in this picture is that the cost of healthcare growed almost to 17% in GDP for the last year. And according to my power law prediction, will reach 25% in about 10, 15 years. This is really bad because it can kill an economy as it is. But what is more important is that out of these costs, many of them are caused by chronic diseases. And when we have to tackle chronic diseases, we have to do two things. First, we have to understand what are the principles that cause these diseases. And second, we have to find the right mathematics to cure or to treat these diseases. In what I'm going to talk about now, I will talk about the mathematics to describe this, in particular, blood glucose dynamics. But another problem that I'm interested in finding out what are the principles that lead to a disease. That I will be happy to talk about offline. So if we look at diabetes, we will see that it is this astronomical number. I don't know if this tells you something, let's say $174 billion. But this number is as big as, or it gets bigger and bigger with years. And it almost gets closer to the amount of profit the semiconductor industry is making. So basically, you have on one side somebody that produces money, and on the other side, somebody that wastes all this money on curing only one disease. But why is it important to understand diabetes and understand blood glucose dynamics is because it leads to many situations that makes us, let's say, inefficient. So it can lead to blindness, it can lead to kidney failure, it can lead to fatigue, so we are not as efficient as we want. So in this problem space, we would like to develop, let's say, an artificial pancreas that can understand what is the profile of the blood glucose, understand what are the interactions with the insulin, and then for those that either don't have a good balance of glucose to insulin, it inserts the right amount of insulin to maintain it within a healthy range. So this picture is meant to give you an idea of how the artificial pancreas works and to highlight a few problems that are important. One problem that I have to mention from the beginning, and I think is still unsolved, is the problem of estimating the right profile of blood glucose that exists in the organism, because relying on a single measurement on one hand is not the best approach. So for instance, we can have continuous glucose monitors, but because the glucose monitor is set on this arm and I'm sitting on it, the reading might be an error itself. So there is, of course, this fusion problem or data mining problem to find the blood glucose dynamics profile. And then the second problem, which I will talk about, is how from these measurements you can construct a mathematical model of the glucose dynamics and then determine the amount of insulin that you have to inject. So if we look at the control approach that was developed in this for the artificial pancreas, we will see that there are two schools of thoughts. The first one relied on the proportional integral derivative controller, the one that is at the top of the slide and is probably the first one and also the most investigated one. One of the big leaders in this field is Gary Stale, to my knowledge. And the second school of thought is based on model predictive controllers, which treats the insulin dynamics as a memoryless process. And basically solves an MPC problem subject to this state equation. The problem with both of these approaches is that if we were to look at the clinical studies, we will see that they talk about this problem that they present the hypoglycemic risk. What it means this is that the these controllers decide about a certain amount of insulin. They inject the insulin, but from the moment that the insulin is injected to the moment it takes effect, there is a certain delay that depends from person to person. So in many situations, the controller has the tendency to inject more insulin than needed, and then that will push the blood glucose to very, very low level, so hence the hypoglycemic region or the hypoglycemic risk. Now, you can ask what is the problem with that. If the blood glucose goes to a very, very low level, then not only that you feel very, very tired and you faint, but if you are driving at that point, you can cause an accident. It can go as low that you can die as you are without even being the driver of a car. Another problem that was highlighted by the clinical studies is the inaccuracy of capturing the blood glucose variability, and I will show that in a couple of minutes. And the last one you see over there, the inter and intra-patient variability. So I choose to show 3 snapshots that come from 3 journals that belong to 3 different, let's say, academic or 3 different research communities. The first one comes from the clinical studies. You see over there the Journal of Diabetes Science and Technology. And if you go to this paper and you read the entire paper, and it's really useful to read it, you will see that the last sentence with which they close the article is that while modern predictive controllers were really good, they were not very good at controlling or predicting the post-breakfast glucose dynamics. And so we need control algorithms that are capable to maintain the blood glucose in the normal range. While for the nighttime, when nothing really happens, or we can assume that not much happens in the body, is fine. In the morning, the control is not as good. Then the second snapshot, I choose to bring it from the Nature reviews on endocrinology, and Roman Hovorka is one of the leaders in this field. And again, there are many ideas that you will find in this paper, and very, very interesting, especially for the people that are doing control. But the last sentence with which, or the last few words of the article, again, highlight the fact that we do not have very good control algorithms. And then I was doing this research, and I found by chance this article that comes from the applied mathematics community to the world of pharmacology. And again, I strongly encourage you to go to this article. You will see that the last paragraph closes with this idea that the ultimate aim of developing models of diabetes is to understand the dynamics of this complex network between blood glucose, insulin, glucagon, and so on. And if we understand how these complex networks evolves over time, how different nodes interact with each other, we will be able not only to control better a biological system, but also propose better treatments. So I choose to challenge the whole community that was developed since the 70s on this, let's say, biological control. And like I said, I took data like Newton would take the apple and throw it from the tree. And I look at the blood glucose over several scales. So if you look at the pictures on the left-hand side, you will see that the blood glucose at the bottom represents the glucose over hours, then days, and then week as a time scale. And what you can notice is that there is some kind of repetition, some kind of pattern that goes up and down, and so on. And of course, there is the time-dependent behavior as well. For a mathematician, this will kind of hint towards the idea of having to deal with a fractal or a self-similar process. And one way to do it, one way to see it better is to take the increments. So what I choose to do in the middle is to take the time series on the left-hand side and do a simple differences. So basically x of k minus x of k minus 1. And you get the increments or the differences in the middle, which if you look at them, they don't really, you cannot distinguish one from the other. So if I were to hidden from where they were coming from, you wouldn't be able to see. So that is a way of saying that you observe cell similarity at different scales. The last few plots on the right-hand side point to the fact that, of course, you have the time-dependent behavior because the mean, the variance, the kurtosis, and so on, they are time-dependent. But also the fact that there is a non-Gaussian behavior, which for the time being we should postpone its discussion. So if we were to deal with these fractal processes, the natural question is if we have a mathematical theory to not only quantify whether a process is fractal, but also to describe it in terms of equations. And luckily, these processes are not only processes that appeared in a couple of years. They appeared a long time ago, so people studied turbulence, phase transition phenomena, and so on. And we have developed certain tools in certain parts of mathematics or mathematical physics. One way that I want you to remember is that we will talk about fractal behavior. And this fractal behavior will be represented either by this time series, which displays self-similarity like the picture in the middle, but also this kind of spiky behavior in the inter-event times. I don't want to stress too much this because it will appear later in the presentation. One problem with this fractal behavior is because here, in this point, if I went to construct a mathematical model, in this point over here, I will be able to construct an infinite number of tangents. And so constructing a model of this sort with integer calculus will be very, very hard, because almost every model will look as good unless we have some hints about the model. In a way, this is why we have to construct schemes in which we do not only measure the difference between the data and the model, but also consider some kind of complexity of the model. But then the question is, how do you quantify in a right and true way the complexity of the model? So we'll talk about fractals and we'll talk about fractional calculus, and this is just the summary slide. So what I understand by a fractal? By a fractal, I understand an object that has this similar structure, some form of repetition. And then the second characteristic that needs to be satisfied is that the fractal dimension needs to be a non-integer number. Just to provide you a historic representation, right here you have the picture of Andrei Kolmogorov, who firstly hinted the scaling laws and self-similarity when he studied turbulence, and he studied turbulence for almost 20 years. And right here you have Benoit Mandelbrot that actually laid out the foundations of fractal geometry. So right here you have a picture of Euclidean object, which definitely is not a fractal, because as I zoom in or even zoom out, the object that I'll get will not resemble to the object that I started with. However, right here I have a pattern that I repeated several times, as you can distinguish here, and whatever I get here will resemble to the object that I started with, and this will be an example of a fractal. And I choose to show it because certain people that were exposed to VLSI can easily think about the H3 clock that distributes the clock on the chip and so on. So the next question is, how do you compute the fractal dimension? And this can be done very easily. Even we can do it before high school because we can easily compute the ratio of two quantities, the logarithm of the number of self-similar pieces or the number of patterns that repeats, and the logarithm of the magnification factor or the scale at which we analyze the system. So on the left-hand side, I choose to show an example of a non-fractal object, because the fractal dimension is integer. So you take a segment, you divide it into 10 equal pieces, and you will find out that the fractal dimension is 1. Right here on the right-hand side, I will take the same segment. I will divide it into 3 pieces, but equal pieces. But then I will always remove the 1 in the middle, like here, then here, then here. And then the fractal dimension will be less than 1 because I have this empty space that I lose at each iteration. So there are many ways to find fractals. One example are trees. You can also think of fractals as the bronchial tree, the brain network, and so on. So the next question is, how do you capture this fractality? And I have to be honest with you, in many situations, we measure that something is fractal, but we stop at that point. We don't go further and describe or determine the dynamical equation. So there is a theory which is somehow forgotten in the library that is called the fractional calculus. And I want to think about it from the simple things. So think about numbers. Think about the fact that we can raise numbers at fractional number, like x to the power 1 over 3. And the natural question is if we can talk about operators in the same way, if we can talk about fractional operators. And this question is not new. It's at least 350 years old, because these two great mathematicians that we learned in high school already debated about the significance or geometrical significance of this fractional order derivative. So just as a gentle introduction, think of the fractional order derivative as a convolution of your function of interest, y, with a memory kernel. And our memory kernel will be of a power law form, this delta t to the alpha. Now, bear with me for a couple of slides. You will see later the reason for which I choose alpha to be time dependent. And to provide you some intuition of the difference between the integer and the fractional calculus, right here we will have the first order derivative of a linear function x, which we know that is the step function from, let's say, control system theory. And then we will take the fractional order derivative of these orders of the same function. So what you can observe is that it has this divergent behavior. And if you flip it up, then you will get a curve that kind of converges very, very slowly to 0. So we'll bring you to, or will make you think about the power laws. So I was very happy to apply this to the blood glucose, and I was hoping to see a nice monofractal, or to see that my blood glucose is characterized by a single fractal dimension. The only problem is that the biological system is much more complex, and when I looked at blood glucose time series, I have seen that they are characterized not by a single fractal dimension, but by many. And in this picture, on the x-axis, you have the fractal dimension that can be exhibited by the time series. And on the y-axis, you have the so-called multi-fractal spectrum, which you can think of it as the distribution or the probability of observing that fractal dimension. So of course, in this picture, the fractal dimension that is around 1.05, let's say if I see over there, will be the dominant one. But it's very likely that I will also see a fractal dimension that is around 0.8, or one that is around 1.2. So this set me off a little bit, because I was expecting a certain type of model. The type of model that I was expecting was something much simpler than this, was d alpha y at dt alpha equal with a times y plus some coefficient. So in order to capture that kind of distribution, or some kind of that variance that I see in alpha of t, then I had to make this order time dependent. And of course, you can ask how wildly this coefficient can vary for someone like us. And the graph on the right-hand side shows that alpha can start, let's say, at 0.4. A couple of minutes later can decrease all the way to minus 0.4. And then a couple of, let's say, 40 minutes later can increase all the way to 1.4. So think of minus 0.4 as a cumulative integral behavior, and think of 1.4 as an oscillatory behavior. So probably in that region, the person is both eating something that is very sugary and doing some exercise. So I'll not have time to go into the discussion of this, but basically these parameters can be estimated in linear time using wavelet techniques. The thing that I want to point out is that how good the model captures the trends of the data. So I choose to show how the model that you have seen on the previous slide captures the hypoglycemic, meaning low blood glucose, like the one on the left-hand side, and hyperglycemic, so basically high blood glucose, the one on the right-hand side. So overall, we capture the trend pretty well. There are certain small spikes over here, that we do not model very well. But when we compare with autoregressive moving, yes, yes.
With the variability in the blood glucose fluctuation, is it like normalized for diet, or is everybody on the same diet?
It's a very good question. I do not remember. So this was measured for a small kid that was suffering from type 1 diabetes. So I think he was already on the diet. So the production of the data was not responsible. We can go back to the database and check if, but I think it was under diet. Yes.
But it's the same every day.
Not the same every day, but probably the same amount of meal and kind of the same type of meal every day.
And then also, so you're fitting this model, and it looks like almost exactly the model. How do you know that you're not overfitting it, or what are the parameters that you're?
So I'm not taking the whole data and fitting the model. I'm taking a window of data, fitting the model, and do a one-step prediction. Okay. So this picture would show you how well we do with the ARMA, the autoregressive moving average model. So what we have done, we take the blood glucose on the left-hand side. We fitted ARMA of several orders from, let's say, order 1, 2, 3, 4, all the way to 40, because I think that is the highest number that we consider. And then we choose the best ARMA, and we put into the mirror with our model. So the picture on the right, on the middle, it shows the estimation error for the blood glucose. And you see that in certain situations when there is like a sudden spike in the time series, I have a huge error in ARMA. I also have a spike in error for the model that I propose, but this error is much smaller than in the ARMA case. What is? The input is this time series that you see on the left-hand side. So this is the input. This is the estimation error, and for the ARMA, the best ARMA, and this is the estimation error for the fractal model with only one fractal coefficient.
So what's the output then? I guess I'm trying to figure out
the output is, so basically we wanted to see how the estimation error for the best ARMA will look with the estimation error of the fractal model. So basically the graphs on the right-hand side would be the output.
So I think what you mean, you only feed until a certain time, then you do a prediction.
Yes,
feed, so
yes.
Oh, the error is in
The error is,
until a certain time, and you release a prediction for the next time step, and then you compare it to the real.
okay, so it's not like a plant model that you're modeling with some input.
No.
The error of the output.
No.
So it's just the prediction error.
Exactly. Yeah.
Okay.
Okay. So the next question was how we should do control. So I will not spend time how the problem is formulated. We can take that offline because I want to spend more time with the other part that I'm more interested in. But what is interesting is that we fitted the fractal model into the data. Then we solved the model predictive control problem with the best autoregressive moving average model, and then we apply that control signal to the fractal model, and that is given by the green curve over there. So what you see that and then what we have done for the same fractal model, we have solved a model predictive control problem in which we have assumed the same cost function, except that we removed and replaced the state equation that was previously described by an autoregressive moving average model and replace it with a fractal equation. So once we apply this control signal, we'll see in the blue line that the blood glucose will start, let's say, at a high value of 210, and will inject the insulin to bring the blood glucose level to about 85 milligrams for deciliter. Now, if we apply the non-fractal control signal to the fractal system, we will see that it overshoots initially slightly. Then it goes down. It crosses the reference point, which was 85 milligrams per deciliter, if I remember correctly. And then it decreases, and it goes in this dangerous region. Now, it is dangerous because if I go lower than, let's say, 50 milligrams per deciliter, then this person will be close to dying, or at least fainting. So we also try to see how robust the algorithm is. So the fractal controller results are shown here, and the best autoregressive moving average type of investigation is shown here. What we have seen is that we stop at 65, and in this particular case, this one has a higher chance to push the patient into a lower values. So for the second part of the talk, I want to focus on lessons learned from this work. I was not satisfied with the strategy of identifying a model by taking the difference between, let's say, the data and the model and so on. And I will try to build a model from the data as we go on. So just a few words about the data. I will use time series from real system from the Intel single-chip cloud computer, which is a network-on-chip multi-core platforms. It is a 4x6 mesh NOC. You have here tiles. In each tile, there are two processors. They exchange messages. They exchange data through message passing model. And then I choose the shared memory as well, because there is a debate sometimes like how you should model message passing systems or shared memory systems. There are certain ways in which you can quantify the performance of these systems. You can quantify the performance in computation either by recording the instructions per clock cycles, the cache misses, and so on, or you can record the performance in communication through node-to-node latency and so on. But what is really important to see here is that all these workloads display very dynamic and very different and complex behavior. What happens when you move and you actually look at the literature that deals with traffic modeling and so on is that they either build models on queuing theory, assuming certain Markovian type of models, or they do some kind of fractal analysis and they are telling you that a certain trace is multi-fractal or a certain process is multi-fractal, and they show this curve and that's it. But this is not very useful for somebody that wants to do optimization, somebody that wants to do traffic engineering, somebody that wants to do network design and so on. So what I want to emphasize and to convince you is that it is very important to take a geometric perspective of this time series. And two things are really important when you construct dynamical equations. One is the interval of time or inter-event times, T2 minus T1, which is the amount of time that passes from when this process was in this state and switched to another state. Then the second quantity is the so-called magnitude increment, whether it is positive or negative. And I will clarify in a second why we talk about positive and negative. Now, why the increments are important? If the magnitudes of the increments are exponentially distributed, then you can easily Taylor expand it, and you can take only the first term and resort to the linear type of equations. And if you want, you can consider some kind of a correction term based on the variance, and that's it. Well, if you analyze the magnitudes of these increments and you find that they are not fitted by the exponential distribution but by other distribution, then this is a sign of how much nonlinearity you should include in the model. So if we go back to the type of models that we want to build in control theory, like dx over dt equal with f of x, u, t, then this will tell you what nonlinearity should be captured in that function f. Now, the second component, we have to analyze the inter-event times and their distribution. If the inter-event times are identically distributed and exponentially distributed, then we can justify the Markovian assumption and we can go on with dx over dt. However, if the inter-event times are not exponentially distributed, but let's say power law distributed, even a composition of power laws, then you have to replace the classical derivative dx over dt with a fractional order derivative, which will be d beta x over dt at beta. So that's why we have to make the distinction between short range and long range dependence. Now, in many situations, especially in stock market or in social systems, we will have asymmetric behavior, meaning that there will be a huge jump in a certain process initially, and then the process will die out much slower. So in that situation, you will have positive increments characterized by a distribution and negative increments characterized by another distribution, which will set you completely off to a completely different dynamical equations that you were to construct if you were to ignore this feature. So in this particular case, if we only look at cache misses, we find that the positive increments are characterized by an alpha stable distribution with 1.56 as alpha, and the negative ones, if I remember correctly, it's about 1.45. The inter-event times, and let me explain first this picture. So basically, on the axis is the inter-event time as it is recorded. And then on the y-axis is the probability that you will observe an inter-event time greater than a certain threshold. The orange circles over there represents the empirical probabilities, and the red dotted line represents the maximum likelihood fitting for the exponential distribution. What you observe is that there is a very high likelihood that I will see at least, let's say, 10 to minus 2, that I will observe an inter-event time greater than 60. While if I go by the exponential distribution, then that will predict, let's say, almost 0 probability. So it is very important to characterize this one because it can tell you a different mathematical model. So the way we do modeling or system identification currently is you take the time series. You start with a simple mathematical model. Let's say the simplest you can think of is ARMA. This is just for illustrative purposes. Then if you are not satisfied with the fitting, then you increase the order, you throw more parameters, and then you end up with a model. And then if you want to kind of have a balance between how well you fit, prevent overfitting, and so on, you will also consider a complexity measure, whether you take into account the archaic information criterion or some other information theory metric. But none of these schemes are actually telling something about the data. And the interesting things that a certain type of magnitude and a certain inter-event time is actually caused by certain events that were in the past. And the other thing is that none of these schemes actually preserve the causality, because it takes the whole data and fits the model for the whole data. So what I want to say that is, if we ignore these mathematical characteristics in the magnitudes and inter-event times, we'll end up with the mathematical models that are not right for that data. If we need to capture the long-range dependence, it's not that we need more and more terms in the model. We might need actually only one term, meaning one coefficient, the fractal dimension, and then fractional order derivative as a way to capture that memory. So think of that. Think of this efficiency. The other one, the nonlinearity, we already highlighted. So the way I postulate that we should construct mathematical models is to start from the total probability theorem. So you want to quantify the probability that the process will be in a particular state, let's say in state X at time t, assuming that the two things that I'm interested, the magnitudes of the increments and the magnitudes of the inter-event times, are characterized by two fractal dimensions, alpha and beta. And for the time being, I'm not making an assumption whether these one are integer or non-integer. So we proceed further, and by the total probability theorem, that will be the probability that I started in a certain initial condition. And then I have to integrate from, let's say, the initial point to the current point t over all the possibilities. So that's why I integrate from minus infinity to x and from x to infinity. And the reason I split it into two is because I wanted to capture this thing that I have seen it in the real data, because certain positive increments are distributed differently than certain negative increments. So one thing that I want you to observe right here is that if I don't have any time, any dependence on the shifts t minus tau, then I kind of retrieve the Markovian case as a particular example of this equation. Now, if we go to the Bible of fractional calculus, we will see that every mathematician that worked on fractional calculus defined their fractional order operator. And in this particular case, there is this fractional order derivative, which is called Ries-Feller. And the good thing about this one is that it captures the asymmetry in the process. So right here, I have the first part, which looks, let's say, at positive increments, and then I can capture the power law exponent as alpha plus theta. and then I can look at negative increments as alpha minus theta. Now, I can only justify this situation if the positive and negative increments are characterized by alpha stable distribution, by asymmetric alpha stable distribution. And you can easily see that alpha that appears in alpha stable distribution can be linked with the coefficient from the formula. And also theta can be retrieved or can be linked with the coefficient of which is called skewness from the alpha stable distribution. So the way you proceed from the total probability theorem is by recalling, let's say in this particular case, I recall the formula for the Riemann-Liouville fractional order derivative. So basically right here, let's see where is my cursor. Okay, so you have to follow me. I don't see it where it is. Okay. Okay, so I have this probability, which appeared on the previous slide. Now, I substituted that W of x minus y, t minus tau with two functions, one that depends on this shift and one that depends on the time. But because I observe a power law behavior of t minus tau to the power, let's say, beta minus 1, then I can express this in operatorial format as the fractional order integral. Then I can use this inverse relationship between the fractional order derivative and fractional order integral. So it's actually like in algebra that we have done it in high school. And then I can apply to the left-hand side the fractional order derivative. Now, one more step that I will do here is that in many situations, you have seen that the time series or the processes are not characterized by a single fractal dimension, but by a distribution of fractal dimensions. So instead of just using one beta, I will have to integrate over the distribution of beta, and that's why I have this h of beta. And right here, I'll have a summation of several fractional order derivatives, which capture the memory of the process, weighted by how important or how likely is to see this in the data. On the right-hand side, I will, after some algebra, I will get this expression, where again you can see that I assume that I have a distribution of fractal dimensions alpha that characterize the magnitudes. Now, how is this related with this equation that you have seen here, or you have seen already in, let's say, queuing theory or in physics? If I make beta equal to 1, and I assume that h of beta is delta function for beta centered in 1, and the same I assume alpha is equal to 1 and g of alpha is again a delta function, then the whole equation will reduce to the classical diffusion equation that you have seen many times in physics. So why is this equation is useful? Well, it is useful because if I know the dynamical equation for the probability, then I can compute almost every metric. So for instance, if I'm interested in what is the differential equation for the mean of the process, then I will multiply with x to the left-hand side the whole equation, integrate over the space of x this diffusion equation, and determine a differential equation for the mean. If, for instance, I'm interested in the probability in the probability that this stochastic process x is greater than 5, then I will integrate between 5 and infinity this equation. I will get a differential equation for that metric as well. So basically, this is a way that you can construct the state equation from the data without postulating a mathematical model, because the data will dictate what kind of transition probabilities W you will see in this equation, and what kind of derivatives you will see in this equation as well. So after doing this algebra, the differential equation that characterize the kth order moments, which have definition over here in the middle of the slide, if I have so right here, is given by this equation. So you see here how h of beta comes into the picture and affects the dynamics of this mk. Now the next question is how you can actually use this in a control setting. And you can proceed exactly how you do it in model predictive control. So let's say, you assume that your state equation should not deviate from a certain reference. You want to minimize the control effort. And instead of using dm over dt equal with am plus bu, then you will use a new state equation of this form. And you can also put constraints on the state variable and control variable as well. Now, I will show you one particular example to show that this works. So what we do here is we take a network on chip. So basically, processors and routers on a chip can run at different voltage and frequencies. We collect in a distributed function and estimate the parameters of each component. So basically, we estimate this kind of model. Then we take the reference values that we want to enforce. So let's say a certain utilization for all the queues that will enforce that we have a certain latency and a certain performance on a chip. And then we solve a model predictive control problem that is kind of similar to the classical MPC because we have the same cost function, but we have a fractal state equation. So how good this is? So this shows for a couple of applications that showed very good behavior. So I choose to solve the MPC with a non-fractal, so basically fitting an autoregressive moving average equation. And I have about 5 to 10% savings with respect to the monolithic platform in which every processing element and every router runs at this frequency, 2.66 gigahertz. Then what I have done, I have constrained h of beta to be a single point. So I want to fit only a monofractal state equation. And I increase my power savings sometimes by 2x. And then I allowed the time series to dictate to me how many fractional order derivatives I should include in the model. And in certain situations, I will increase the savings up to 5 times over the ones that are in a non-fractal case. So one good thing is here is that I have better predictability. But one bad thing is that in certain situations, I will need to estimate about, let's say, 50 fractional order derivatives, which might not be so is not as bad as in non-fractal case, but it doesn't translate in too much savings. So I have seen that in one particular instance. So in closing, I want to summarize some work that we are doing currently. So we want to study complex interdependent networks. So basically, you have a network here that interacts with another network here. In this particular case, you have the brain network that works with the muscle network and dictates the way in which you move the arm. So we collected data when the individual is doing about four actions, the ones that are shown on the right-hand side, extending fingers, flexing fingers, and rotating the hand. And then what we want to see how the two networks interact with each other. And the mathematical model that we are looking for is of this form. Now, the beauty of this mathematical model is that in certain situations, there will be certain processes that are fractal, that would have memory. And in other situations, there will be processes that they will have no memory. So right here in this matrix, over the diagonal, this will be the fractional order derivatives. And some will have the coefficient alpha close, let's say, to 0.5, while others will be close to 1, so the classical memoryless equations that we are dealing with. The nice part is also here on the right-hand side. This matrix will encode the couplings or the interactions between different networks or between nodes belonging to different networks. The nice thing about our results was that the network that we identify, for instance, when we extend the fingers, retrieved the network that was advanced by the anatomic book. Except that in addition to that, we can also quantify which are the nodes or which are the muscles that are really important, and with what interaction or with what coefficient of interactions affects the dynamics of other muscles. So in conclusion, we are trying to develop a data-driven mathematical modeling in which we try to estimate the state equation from the data. We don't try to postulate a particular expression. And the next step is, of course, to see when you are actually estimating the right model and when you are when you are actually overfitting. We have learned something from the blood glucose, and looking at the real data made us think about new controllers such as the time-dependent fractal optimal control, which was not considered in the literature, and the multi-fractal model predictive control. Right now, as I mentioned, we are not only looking at correcting the pharmacokinetic model, so basically how the insulin is affected by certain biological processes, but we also try to find out how should we identify the models when we don't only have one process like the blood glucose, but have different networks like the brain and the muscle. So in conclusion, I want to thank to my PhD student, Yong-Kun Xue, who has contributed a lot to this work.
Are there any questions from the audience?
I'm still confused on how you would apply it onto like an online controller, because it's very clear that you can get the characteristics of actual behavior and of all the statistics on it.
So very good question. So basically, this is the thing that I have skipped in the presentation. I said at some point that this can be done online, but I didn't say how. I just said that we use wavelets. Well, the way you do it is like this. You will have some kind of filters that will look over the time series at different scales. So let's say I look at scale 2, 4, 8, and power of 2. Now, when I have about 1,000 samples, if I want to fit the model, I may be required to solve a linear regression with a matrix of 1,000 by 1,000 with 1,000 variables. That's huge, right? But if I look over and work with the wavelets, then I will only need at different scales. Scale 2 at power 1, 2 at power 2, and so on. So in the end, I have about 8 variables that I have to estimate. So instead of solving a linear programming problem, let's say, with 1,000 variables, I'll have to solve an LP with 8 variables. So that's the efficiency that comes. Now, you will say, how do you do this online? I do it as the sample comes in. If the sample is a power of 2 to the 8, then that will affect my coefficient for that scale.
Sorry, say that again.
So let's say this is the 8, or let's make it smaller. So this is the 4th recording. That will affect only to the coefficient of variation that appears to the power 2 to the 2, right? Now, if I go to the 8th element, that will affect only that. So it's like you do only scale-wise. For each scale, you compute a coefficient of variation or a coefficient that measures the fractality. And then you don't take the whole 1,000 samples, but you only take the wavelet coefficients.
If you're doing online control, I mean, because I think you could do really conservative methods, right, where you just make sure that it works despite these huge.
But there is a one catch. So for instance, right here. So right here, when I have to estimate this W, I don't need to do this estimation of the W in the time domain or the domain of this. I can apply the Fourier, the two-dimensional Fourier transform, and I can fit the joint PDF in the characteristic function. So rather than working with 10,000 samples, which is huge, I can work with 100 frequencies, which probably it would be too much. So I can even consider less frequencies. But I can do a significant pruning of the estimation problem. So actually, for this one, to fit the alpha stable distribution, I don't have a closed formula, as we know I don't have the marginal. But I can work with the characteristic function.
Yes, I have one question. So if we take a Fourier transform of a signal with some type of fractal characterization, like, what should I expect to find? Like, because the scale invariant aspect of
so for
signals.
Instance, once you take the Fourier transform and let's say you compute the power spectrum, so basically the modulus, then you will observe a scaling behavior of f to the power that is related with the fractal dimension. It is the so-called 1 over f to the beta behavior that you might have seen 1 over f behavior in internet traffic as the title of some of the papers. So the moment you take the Fourier transform of a fractal process and you compute after that the power spectrum, then you will observe as f to minus beta. And that beta should be far away from an integer number. Now there is a catch, because if it is getting close to 2, then there are pronounced non-stationarities, and then you have to deal with different tools, because the power spectrum is not well defined. So in that situation, you have to go and work with determinate fluctuation analysis, another method that I think we discussed it in the morning, in which you fit trends over different scales, and you compute the fluctuations from scales, and then you look if the fluctuations have some kind of power law behavior, which is reminiscent of a fractal behavior. If you don't see then that power law behavior, then you don't have fractal behavior.